Hey there, my name is Dan. Hope you're enjoying the conference thus far. I am going to be telling you a little bit about a Cosmos DB use case at Walgreens. So with this, I'm going to be speaking to expanding the bulk patch functionality with Walgreens, especially using Apache Spark. Jumping right into it, my name is Dan. I'm a resident solution architect at Databricks. I've been at Databricks for over 3 years. So what I do at Databricks is I help customers be successful implementing data pipelines, and that can require gathering requirements, making architectural suggestions, or implementing architectures, hands-on coding, as well as the documentation, testing, everything else, managing other developers. I'm a really big fan of the data lakehouse paradigm, which Databricks sort of pushes. So I think that the best data warehouse is a lakehouse. Make sure that all of your data is in open file formats and easily accessible for BI, ML at scale. So I'm a big fan of Spark Structured Streaming, running data pipelines, Delta Lake, Scala, functional programming, and the autoloader ingestion framework. If you haven't checked that out, you're a Databricks customer, definitely recommend it. It's super slick. So I can give you a little outline for my presentation. First thing I'm going to talk to you about, what was the Cosmos DB use case at Walgreens? It's with their prescriptions. Then I'm going to tell you about the proposed data pipeline architecture that we set up. Then afterwards, I'm going to go into some of the complex issues that we faced. And some of the stuff is going to be super technical, but I'm going to go through it fairly fast. So first, I'm going to go through some of the known complexities that we had coming in that were just artifacts of our architecture. Next, I'm going to go into how we solved one of these in detail, which was expanding the bulk patch functionality, the namesake of this presentation. And finally, I'm going to talk about some of the unknown complexities. And these are the things I really encourage you stick around to see these, because I wish I had known these things when I started this project. They were definitely caused a lot of last minute changes during integration testing. So hopefully you don't have to run into the same issues. So let's go into the use case. So the idea here for this project was that we wanted to make the on-prem prescription data available to the Walgreens Pharmacy mobile app. So for instance, let's say that you have a prescription, you should be able to look in the app and be able to see, this is when the doctor sent this is when it's available for pickup, this is all my prescription history. All that needs to be accessible at a 1-second lookup time SLA. In addition, the requirement was that we needed to make sure that we had a 2-minute end-to-end SLA coming from landing in the centralized data warehouse going into Cosmos DB. So we chose Cosmos DB for this really because of that 1-second lookup SLA from the mobile app. Since Cosmos DB is geographically distributed, highly concurrent, multiple users can be pinging Cosmos DB to get the information for their prescriptions and refill histories. Other requirements is that the data need to be processed in the correct sequence. So this is essentially a change data feed sort of pipeline. So if we process things in the wrong sequence, sometimes we can have data loss, which we want to avoid. Another big requirement is that everything is going to be end-to-end voltage encrypted, which is something that made things a lot easier from the developer side nominally. But, and this is something I'll get into a little bit later on, it actually caused some pretty big hiccups from the Cosmos DB side. So next I want to go into the data pipeline architecture that we proposed for this. So as I spoke to before, everything is landing in Oracle, which is on-prem. It's a big sort of legacy system that's handling all of these sort of transactions coming from new prescriptions, new fills, all the different details. This is going out as a change data feed into Kulik. And then Kulik replicate is being used to send all the change data into Kafka. Into Kafka, the data is normalized. It's split into 5 tables. These tables include different aspects of, this is the prescription with its, this is the medication and the patient ID. This is the fill information is in another table. The exception information, like for instance, if there weren't enough of some medication somewhere, or they had to make some sort of change, some exception is going to be another table, and then other details are covered by other tables. So what's happening basically in this pipeline is the information is coming in a normalized format, and then we're writing it to Cosmos DB in a denormalized format. So the idea is that everything's going to be into one big nested schema. And so when the mobile app needs it, it can go to Cosmos, just get the information it needs, don't have to do any additional joins, and then serve the data to the customer. So the way that we do it, and this is very simplified for our architecture, is for each table, we get the Avro encoded data, then we use the Confluent schema registry to actually decode all of that Avro. Then we roll it up. I'm going to go into roll up in a subsequent step, but the idea being for each table, we might have multiple records per microbatch. So we need to roll it up so that we don't only do one write or update per microbatch for each primary key. And then after that, we're going to do our insert writes and our update writes. And I have those actually separated out because we needed to use a different API for those. The inserts, we could use the upsert of the item patch API. The updates, we actually had to do ourselves. Finally, you can see that there's two collections in Cosmos. There's two collections because we wanted a really fast lookup time. The trade-off we made is we wanted to throw a lot of resources at it and actually duplicate our collection in Cosmos DB, but just with different partitioning schemes. That way, the microservices could actually pick these up very quickly. So let me talk a little bit about the known complexities. So this is a representation of the table as it comes after everything is brought in from Kafka. You can see that the different tables are going to have different entries as different rows. And in addition to that, we're going to have different CVC operations. If you see, like for instance, with this one, these are two of the same ID, like the same primary key, but they have different CVC operations. So the first thing that we had to do is set up the aggregation logic. For the aggregation logic, we'd actually need to combine these two rows to be one row because we don't want to go through and for every single row write something to Cosmos DB. We'd have to worry about ordering. And also that'd just be a lot of writes. Instead, we want to aggregate it so that for each table and for each primary key, we're only going to have one write to Cosmos DB. So in this case, this insert and subsequent update would turn into just a new insert, but the records would be null A, null H, which is combining the data from both. So we solved this using the aggregator API with Scala Spark, which is basically like a newer version of user-defined aggregate functions. The other thing that was pretty hairy, and which I'm going to go into the code for, is how we handled partial updates. So the problem with these like CDC data is that when we get an update, we don't get the full record, right? We just get a partial record. And you can see that there's this change mask here, which is 1100 ellipsis. What this means is that the positionally first and second element are actual changes to the data for this primary key. The rest of them are just null, they're just placeholders. And that's just a function of our Avro schema, right? So the challenge faced with this is that if we're trying to update a bunch of these records at once into Cosmos DB, we can't use an upsert, right? Because then it's going to overwrite all of the fields that aren't in there. And then we can't really use item patch either because we're trying to, different rows are going to have different fields that are changing. So how do we handle that? The way that we solve this is actually by extending the bulk update functionality ourselves, basically re-implementing some of the connector ourselves. Hopefully you don't have to ever go down that road, because I was communicating closely with the Cosmos connector team, the Spark Cosmos connector team, and Fabian. I believe they are going to roll this into the product to be able to use the change mask. But in the meantime, it was really cool, and I'd love to show you about it. So this is how I sort of achieved it. This is a lot of code. I suggest, I'm not going to go everything in detail, but feel free to, if you're watching this down the line, you can stop the video um, and go through it. But essentially what's happening here is we're going to get our data frame, and then we're going to coerce it into a format such that the data frame is usually going to be rows, where each row is going to have a lot of fields. Instead, we're going to explode it. And so I'm manually exploding it into a certain format that I'm going to use to write it afterwards. So basically what happens is I do a flat map to explode, and then I get it such that for every row, row quote unquote, we're going to have an ID, the key, and the value. So that's going to be what's the primary key, what's the field name, and what's the value for that field. And then I have an optional thing for if it's nested, which is basically just a modifier for handling if it is a nested field or not. And then I'm going to filter that based on the change mask. So I'm going to basically zip it with the change mask and then filter based on that value. So after I have it in the Cosmos write row format, I'm going to write it. So to do the write, we actually just use the Java SDK here. So what happens is we have this exploded data frame. We basically are using the RDD API here to where we group it by field. And then for each field, we need to actually apply the correct data type that's in Cosmos, because we can't write them all as string. Some are going to be integer, some are going to be this or that. So we get the data type and we coerce it. We apply the right type to all that data, and then we actually write it at the field level. So the cool thing about that is that instead of writing each row one at a time, which is going to scale based on the size of the microbatch, it might not be that scalable. What we're going to do is actually we're going to do one write using the Cosmos bulk operations get patch items operation API. We're going to do one write per field. And so that's great because it's actually going to be limited to what's in the schema, which in the case of Walgreens was only like 200 or 300 possible fields that could be written to. And then under the hood, we were just using sort of like the Flux API, and we were setting up our own Cosmos connection and executing the bulk operations in async. So that's basically how we achieved it. This is pretty high level. This is pretty low level, but I wanted to give some idea in case folks run into this in the future. So moving on, I want to talk about some of the unknown complexities. So these are issues that came across afterwards. So when we were doing integration testing, we kept on finding error 400 bad request. So one of the reasons why this was happening was because of our voltage encrypted data. If you've ever worked with voltage encrypted data, you know that it actually will spit out a lot of weird characters like / and \. One of the things that we found out about Cosmos DB is that you actually can't have a / inside of your primary key. If you have that, it's not supported in a lot of use cases. In our case, for writes, we couldn't do it. It actually corrupted some of the operations inside of the Spark Cosmos connector. Our solution, we just encrypted everything in MD5. MD5 doesn't have any of those bad characters, so we were good. Interestingly, you should know, there's no restrictions on what's in your partition key. So we didn't have to do any sort of MD5 encoding on partition key, which was it was sort of like a silver lining. It made things a little bit easier. The other thing that we ran into afterwards is that our partition key had to be populated during write and patch operations. So usually when you think of a key value store, you think the primary key is going to be unique across the collection. In Cosmos DB, that's actually not true. It's the combination between the primary key and the partition key is going to be unique. You can actually have multiple primary keys for a given partition key, or you can have multiple primary keys for a given partition key, but across partition keys, you can actually have the same primary key. So this actually was a big issue for us because one of our collections, the partition key, had the patient ID, and the patient ID was only in one of the tables. So to get around that, we actually had to do a big read from Cosmos to get everything before writing, which is something that we were trying to avoid the entire time. So anyway, this is these are some of my important takeaways from this project. Thank you for watching the presentation. I hope that was useful for you. I hope you don't have to deal with some of those issues at the end, like knowing that you need to write with the partition key and the primary key both for item patch, and knowing for the special characters. I hope you got something from it, and enjoy the rest of the presentation. Feel free to reach out to me if you're looking at this, 6 months or 1 year in the future. Feel free to LinkedIn me. I'm happy to talk about anything. I'm happy to hear from you. Appreciate it.